Hello everybody, welcome to this new training on the marine data for Africa. I'm Alexandre Morin and I will be your trainer for this Jupyter Notebook exercise. So today's topic is Africa. So it's a continent with up to 26,000 kilometers of coastline, and it is a continent that relies on its marine resources for fisheries, for instance, but also for transportation or energy. And it is subject to climate variability and extreme weather events. And today we will be studying one of its most influential climate systems, which is the West African monsoon system, which is mostly located in West Africa. So it's a system that drives rainfall patterns and therefore influences agriculture, food security, whether it's on land or in the ocean. And in our case, we will be mostly looking at ocean variables, mostly temperature, currents, and primary production, so chlorophyll, which is correlated to marine biology. And we will be monitoring those variables and trying to look at also long-term patterns, because being able to identify them is a way for authorities, for example, to be able to implement, for example, fishery management policies, or even improving climate models. So in this notebook, we will be working with Python. So here are a few libraries that will be used in this notebook. If you are already familiar with Python, you've probably already used NumPy, for instance, which is great for computing and managing data arrays. Pandas for managing data tables. Xarray is used to open scientific data which comes in HDF5 or NetSDF format. In our case, it will be NetSDF. SciPy will be used to compute statistics and trends. And finally, Matplotlib and Cartopy will be used to draw the different graphs and plots and maps necessary in this notebook, and datetime is great for computing and managing time series. So before you start, make sure that if you are working in the CMEMS Jupyter Hub environment, that you have loaded the CMEMS v4 kernel here, which has all those libraries pre-installed. So here is a brief overview of the products that we are going to use. So first of all, the temperature and currents data will be retrieved from the Global Ocean Physics Tree Analysis, which is available on the Copernicus Marine Service website. So you can click on the link and look at the dedicated page on the catalog to have more information about products. You can read the user manual, for instance, which could be of great help if you want to dive into the different variables that are available. So, but just to sum it up, this is a data that relies on a model, but also uses some observation that are incorporated within the model to have something as close to reality as possible. And here are the variables that we are going to use. Well, the name of the product, its resolution, so 0.08 degrees squares, which is about 8 kilometers. We have daily and monthly data. In our case, we will use monthly data because we will download data from almost the entire period that it covers, which is 30 years. So monthly data will allow us to still be able to compute long-term trends, but still keeping a manageable file size, because daily data will be will yield very heavy data files. And for the biology aspect, so we will retrieve primary production using a chlorophyll dataset, which comes from here, the ocean color level 4 monthly observation. So here it's a dataset that is made strictly from observations. Here you can see that several satellite observations are combined to build this product. Once again, there is a lot of information available, but to sum it up, you can see that we will retrieve the chlorophyll variable. So it has a 4 kilometers resolution, and as before, we'll use monthly data. You can see that it covers a period that is a little shorter because it starts in 1997 instead of 1993. And finally, before we start, here is a brief overview of the Copernicus Marine Toolbox. So basically, it's an API that will allow you to download data from the notebook, directly from the notebook, without using the catalog. So basically, given that you have loaded the CMEMS v4 kernel here, you will be able to import the Copernicus Marine Toolbox, which is this library. And using the subset function, we will be able to retrieve the temperature and currents data and the chlorophyll data. So first of all, what we will do is that we will define an area of interest. So by latitude and longitudes, you can see that, well, you will see that here we are around the Gulf of Guinea. And using this function, you can see that we have our long lat box that is retrieved here, our temporal coverage, the depth that we want to retrieve. So here is the closest depth layer to the surface. We will use surface data. Well, the output directory, and here is the ID of the file that we want to download. So to retrieve that, you just have to go to the catalog. So here we go here. Click on Data Access, and for instance, if you want monthly data, you have the variables here, but more importantly, you have the ID here that you can copy and paste in this cell. So executing this, you will have to enter your credentials, and the data will be downloaded here in the data directory for this training. So we do that here for the temperature and current, and we do it here for the chlorophyll. It is another identifier. So it's all pre-downloaded, but it should work when you do this training at home. So now we have downloaded the two datasets. I propose that we take a look at them. So first of all, let's open the temperature and currents data. So as you can see here, we have a dataset with 4 dimensions. So we have one depth dimension with only one level. We have latitudes and longitudes because, well, it's a dataset covering the Gulf of Guinea. And we have a time dimension because we have data from 1993 to 2020. You can see by clicking here more samples of data. And by clicking here for each variable, you can have extended information by displaying the metadata. So here for temperature, you have a complete name for temperature, a short description, the units. So here we will be working with degrees Celsius. Same thing here for the current. So we have the northward and eastward velocities. Here is the eastward in meters per second. So yes, NetCDFs are great because they are self-descriptive, and the metadata gives you all the information you need when you start playing with the files. So now let's do a bit of pre-processing. As you can see here, we have one depth layer. We don't really need to have this 4th dimension in the dataset. It will probably cause us errors in the next processings. So what we can do is to use the squeeze function. It will erase dimensions that have only one level, so that are not necessary. And you can see here, when I've squeezed the dataset, the depth dimension is now empty. Next, we will compute the total current velocity, combining the eastward and westward and northward, components. So with this simple formula, we create a new variable in the dataset, which we will call current speed. So it's not displayed here, but I can show you live that now we have a new variable in our dataset. Okay, so now that our data is ready, what we want to do now is to highlight seasonal patterns in the data, especially regarding temperatures. So what we're going to do is that we're going to compute 4 climatologies, so 1 per season, using the group by function. So basically, it is very simple to group the data by season. And if we do that, you can see and perform the mean for each season. You can see that now we have a season coordinate and dimension that has replaced the time dimension. And you can see that we have 4 seasons, so DJF for December, January, February, June, July, August, May, April, March, April, May, and September, October, November. And so you can understand that at the time we have performed the average over the whole season over the somewhat 27 years of data that we had available. So now we will plot all of this to see how the climatologies differ regarding temperatures. So this is what we're going to do in this cell, plotting 4 maps, one for each season. And we'll be plotting, so coloring the map using temperatures, and we'll also display for each climatology the current velocity vector fields using the eastward and northward velocities. And this is a result. So you can see that during the, let's say, boreal summer, so during June, July, August, there is a strong cooling of the ocean under the Gulf of Guinea, and especially in the coastline. You can see this blue stain here that shows that the water is much colder in this area than in the open ocean here, or even than in other seasons. So if you want a little explanation, so in this season it's an intensification of the West African monsoon system, where we have winds that drive the surface water here away from the coast, and the surface water that was warm is replaced by deeper layers of water which are colder, causing this cooling near the coast, and we call this an upwelling phenomenon. Okay, so now that we have observed this, we can try to do something which is correlating temperatures and currents and see how the two are related. They probably are. So with X-array, it's very easy to perform a correlation between two variables using the core function. So we will correlate from our dataset temperature and the total current speed along the time dimension. So remember, we have 27 years of data. Computing this, now we have a correlation dataset that is a 2D map with correlation coefficients. If we plot that, what do we obtain? So as you can see here, in this area, we have a strong negative correlation between sea surface temperature and current velocity. So this highlights that in this area there are strong currents. When there are strong currents, it tends to bring colder waters to the surface. So which is kind of confirming the upwelling phenomenon that we have observed just before. But we have also other areas here where the correlation is much weaker, sometimes positive, sometimes negative. So this may indicate the influence of other processes that might not be visible here. And this may require further studies that go beyond this training. Okay, so now we can take a look at primary production, because of course the upwelling phenomenon in West Africa are linked to changes in chlorophyll availability and marine wildlife by extension. So now let's open the chlorophyll dataset. We have it here, our chlorophyll A, which is expressed in milligram per cubic meters. And just like we did before, we're going to compute the seasonal climatologies for this variable. So once again, we have seasonal data for climatologies. It takes a little more time to plot because the resolution is a bit higher, but here it is. And you can see that during the season where we had a colder patch of water in this area, you can see that compared to the other seasons, we have a higher chlorophyll A concentration near the coast, which is consistent with the fact that the upwelling phenomenon in West Africa are drivers for primary production and are important for local fisheries. And of course, it's also consistent with the fact that as deeper water go up to the surface in this phenomenon, they also bring nutrients that were below surface, which is also, of course, a driver for plankton growth. Okay, so now that we have observed these classic interactions between chlorophyll and currents and temperatures in this area, let's try to see if we can find some long-term trends with these variables in this area. So remember, we have the sea surface temperature, the velocity of currents, and the chlorophyll A concentration. So we know that the climate is changing, and trying to see long-term trends over the last 20 to 30 years may allow us to try to gauge the potential impacts of climate change on the region. We know that other currents are, for example, slowing down, for example, like the Gulf Stream. So let's see if we can find something similar in this area. So first thing we'll do is that we'll compute the time series for each dataset. So basically we will average the data over the entire area. So this is what we're doing here. We're using the mean function along the latitude and longitude dimensions. And we had monthly data, and to examine long-term trends, we'll group them by year to eliminate the seasonal component that is, of course, in the data. So we do this for the temperature and velocity dataset and for the chlorophyll dataset. So now we have yearly values average spatially. Okay, so now let's look at first at the current variables. So we have the two components and the total current velocity. And now using SciPy and its linear regression module, we'll compute the trend and its correlation coefficient to evaluate whether there is a decreasing or increasing trend and whether it is significant or not. So we do that 3 times, one for each of the variables, two components and the total current speed. Let's plot all of this and see what we have. Okay, so we have two decreasing trends for the two components taken individually. So you can see, for instance, for the eastward velocity that it is apparently losing 2.2 millimeters per second per year. And so the northward velocity also has a decreasing trend, but which has a much lower magnitude. Both have, well, I would say quite strong correlation coefficient. However, when looking at the current speed here, you can see that the trend is mostly zero and insignificant. And this is because if you look closely at the graphs here, you can see that each time one of the components is low, it is almost always compensated by the other. So here, for example, in 2010, the eastward velocity is very low, but the northward is very high. So in the end, we can't really conclude of anything significant regarding the currents in the Gulf of Guinea. We can see that the total current speed doesn't undergo any significant long-term changes. Maybe some slight changes in direction of velocity, but we can't see anything really significant. Okay, now looking at the temperatures. So we can see here that we do exactly the same thing, computing the linear regression of the temperature data average over the whole area. And here, looking at this, we can see that we do have a strong correlation and an undeniable increasing trend of 0.025 Celsius degrees per year. So here, well, this is well, something that we kind of expected because temperatures are on the rise almost everywhere in the oceans. This rate is steady with some internal variability, which could be due to other processes. And finally, let's take a look at the chlorophyll variable and see what the long-term trends are for it. So same thing here, computing slope, correlation coefficient. There is also a p-value here that tests the hypothesis of whether the data is steady or not. We can always print it if you want to further assess the significance of the results. And looking at this, we have something kind of interesting because so we have a quite low levels in the first year that we can observe. Here a very high plateau, and that abruptly decreases and stabilizes at a lower level here. So here we can't really conclude anything on the trend because obviously it is not linear. We don't have a steady decreasing, but something like brutal. So this could be investigated by gathering more years of data, hopefully further in the past here. But some hypotheses that we can make are that, for example, some other variables have reached a certain threshold that have caused this brutal decrease in chlorophyll A concentration. But of course, as I said, this is only an hypothesis, and first we should have probably more years of data to study to strengthen this result. And also, we should probably look at other variables in this area, in this system, to try to find an explanation and better interpret this result. So, we have reached the end of this tutorial. So you will find here a few exercises you can do. So displaying other variables, showing trends using only key seasonal patterns, for example. Feel free to do them when you complete this training. And overall, I hope that you have enjoyed this session, and thank you very much for your attention. Goodbye.